I'm neither a medical practitioner nor the son of a medical practitioner. As Earl's summarized, I'm a geologist, so my focus on the whole question of the human factors of going to Mars or the Moon is very much from the point of view of a practitioner. We're not going to Mars to study primarily the human body in space, or how people live together in a tuna can for 2.5 years. We're going to go to Mars to study Mars, to explore Mars, to work out how to live there. So all of the human factor stuff, biomedical and so on, is for me a means to an end. So I make no apology for that, but please forgive my bias. Now, come on, aha. All right, so back in 2015, NASA held a first landing zone workshop to identify exploration zones for the first mission to Mars. Key word, zone, not site. When we go to Mars, we'll be looking at zones 100 kilometers in radius, 200 kilometers across, within which there'll be a small landing site, flat and boring, where the spacecraft will touch down, where the station will be established. But from that, people will be exploring out from there. And at this workshop, some 47 sites or zones were identified. You can see them on the map there. And my group, which included Heather Smith from NASA Ames and the late David Wilson from the Mars Society, and also who was working at Ames at that time, identified Meridiani Planum, where the Opportunity rover landed, as our prime site. So the mission priorities that were identified for this workshop, for us to design our landing sites or to categorize our landing sites according to, came around 3 priorities. First of all, safety. Safety trumps everything else. You know, there's no point landing on Mars if you're dead when you land, because it's too rough or too high or whatever. And also safety in terms of surface operations. Not only when you land, but how you're going to move around there. Are the slopes too steep? Is the terrain too rough? And so on. Secondly, resources, especially water resources. Ideally, you need these to sustain the station and the crew from the first mission onwards. And lastly, the science, which is primarily, for the case of that workshop and in terms of the mission goals, is astrobiology. Is Mars inhabited? Was it in the past? If not, why not? Secondly, atmospheric scientists, because of the current focus on climate and environmental change on Earth, the atmospheric conditions on Mars and the climate history of Mars seem to be very, very important. And lastly, geoscience, but not least, because a lot of our searching for features of astrobiological interest, a lot of our information on climate records on Mars, of course, involve the geoscience. So these 3 things fit together. And the background image there is one of Card Emmett's wonderful drawings from the early 80s of a Mars mission from the Case for Mars conference, the second one. And it's one of the few artworks about missions to Mars that actually shows people doing things other than exploring. They're actually setting things up. And this is why this is very, very important. To explore, you really got to find a safe landing site. You've got to provide the infrastructure, the resources and so on to do all of that. Here is the map of our Meridiani exploration zone. The Mars Exploration Rover landing site is shown up there. That falls within a 100-kilometer radius. The site we chose for our actual landing site in that black box was a candidate originally for the Curiosity mission. So we have a lot of information about it. And all those ellipses there are the sites of interest, either for resources or, more importantly, for science targets. And there's a lot of them. There's also some I've indicated just outside as well, if it turns out that we can go.
John, could I just interrupt you? Very apologies. Could you possibly make that full screen, just for a bit easier to read?
Pardon me. I thought it already was. How's that?
Yeah, no, we're just seeing the windows behind it. Thanks, mate.
Thank you. All right. Apologies for that again. Okay, so each one of those ellipses roughly represents the capabilities of an advanced robotic mission, like Curiosity, like Perseverance. So you can see here the enormous jump in capability that having astronauts on the surface provides. And there's things like relatively recent craters. There's ancient uplifted rocks here. There are other features like old river channels that you can sort of see underneath there. And I'll be talking more about that area. And you know, all of the work that Opportunity did was essentially this little spot in here. So the first thing is landing successfully. Here's a ground view of Meridiani Planum from the Opportunity rover. You can see there's bedrock at the surface with a very, very thin veneer of sand. One of the big challenges facing landing large payloads on the surface is the entrainment of loose surface material. That the exhaust from the landing rockets will excavate large holes in soft material, and some of that will blow across the landscape, some of which may well bounce back and damage the spacecraft. So this is a perfect landing site, or a very good landing site, a firm substrate, very little loose material. And what there is of loose material is mostly sand, sand-sized. Also, you can imagine getting in your four-wheel drive and driving across that. Those little dunes or ripples are about 30 centimeters high, perhaps down to 10 centimeters high. So they're no real obstacle to driving around your landing site. Secondly, in terms of atmospheric conditions, you're landing well below Mars datum altitude. So the air pressure is high, which is a requirement for things like enough atmospheric depth to slow down to land. If you're using parachutes, your parachutes will actually work. It also means you have equatorial temperatures. And also we know from Opportunity experience and the design work for MSL that the wind conditions there are within the acceptable parameters for landing spacecraft. Dust devils are very rare. There's an image there from the rim of Endeavour crater showing one of the very few dust devils that was imaged by the Opportunity mission. But because of these atmospheric conditions, it also means that it will meet the requirements for an interesting meteorological site for research. The plains are navigable. We often look at Mars art. We often look at science fiction movies set on Mars, and they're all in this sort of orange glow, like some sort of post-apocalyptic movie of Los Angeles. And in fact, the Mars atmosphere is not that dusty. This is admittedly a good day. The Opportunity rover view looking across the plains of Meridiani to the rim of Miyamoto crater, which is almost 60 kilometers away in one direction, and Bopaloo crater, which is about 55 kilometers in the other. So while there will be sophisticated navigation tools on Mars, the crews driving across the surface will be able to see where they're going and drive straight to it. Really, really important. In terms of rougher areas, because as I'll talk later, there are both lowlands, which are the plains of Meridiani, and also uplands to the south. The crater rims of Endeavour will indicate the sort of terrain that you would find in those uplands. And as we've seen in this photograph, those slopes are relatively gentle and in most places quite passable to exploration vehicles. I'd have no hesitation driving across some of those slopes. And I'm a very cautious driver, as everyone who knows me knows. Water sources. Most of the work that's been done on accessing water sources on Mars is focused on ice. Now, there are good reasons to choose ice, but ice is not everywhere present near the surface, and there's also some disadvantages with using ice too, particularly in terms of planetary protection and protection of crew against possible biological hazards should they exist. And at Meridiani, the plains, as the Opportunity image shows here, are made up predominantly of magnesium sulfate minerals, which are highly hydrated. So in that image there, the Burns Formation is named that rock unit. It's about 20 to 30% magnesium sulfate. And that translates into about 10 to 20% water in that rock. And magnesium sulfates dehydrate for the most part at quite low temperatures. So you could get a ton of that material, which is only about half a cubic meter. You'd heat it up to over 100 degrees, 150 to 200 degrees for the most part, and you would get, out of that ton, you'd get 100 to 200 liters of water. And it'll be sterile. It would be a very high purity, and so ideal for use by your habitat and of course for other uses like making propellant. So there's a good water source there on Mars. In terms of the astrobiology and climate record science goals, Meridiani plains are a succession of very well bedded sediments. This is up to the northwestern part in Danielson Crater. Those beautiful layers are, if you like, the pages of the book of the history of Mars or a chapter in the history of Mars. And those beds are couplets. You can see the highly resistant bits sticking out, the light colored ones, and the dark colored ones, which are less resistant and are covered in sand, blue there, but actually reddish brown in reality. Those couplets are 6 to 12 meters across. Each one of those white layers is about 3 to 6 meters in thickness, 1 to 2 stories, just exposed for people to walk over or drive over. So tremendous record there potentially for astrobiological habitats and for the changing climate of ancient Mars. In terms of the geology, here's a geological map of the region, or the latest geological map for the region. There's a lot of diversity. There are ancient terrains here, over 4 billion years old, in the uplands, and then over here we have the younger ones, about 3.5 billion years old, that form the northern plains. And we've got craters of different ages. We've got ancient river valleys. They're probably feeding out into and perhaps under these plains as well. So there's a lot of geological targets, and all easily accessible to a surface mission. Now, I really like Meridiani. I originally chose it because it was convenient, because we had a lot of data. But I do think, subsequent to the research we did there, it is one of the most attractive sites for landing in Mars for all of those key reasons. Safe, water resource, and scientifically interesting and diverse. But regardless of whether we go there or not, we will have to cover all of those bases when we choose a landing site on Mars. So the methodology, regardless of who goes or when we go, will probably be very, very similar. Well, like I said, I'm neither the son of a medical practitioner nor a medical practitioner myself, but there are a number of human implications evident even to a geologist for the Martian environment at a place like Meridiani, for the biomedical sciences. I mean, first of all, Mars is a comparatively safe place for astronauts compared to, say, the Moon or Earth orbit, or indeed in interplanetary transport. We've got moderate gravity, roughly twice that of the Moon. We've got relatively low radiation, despite a lot of scare stories about radiation on Mars. Inside a Mars habitat, you certainly have less than on the International Space Station. Curiosity rover at Gale Crater has measured surface radiation as being unshielded surface radiation as being about the same as inside the International Space Station. There are local life support resources available. There's stable infrastructure. What do I mean by that? Well, the International Space Station is a dynamic environment. It's orbiting the Earth. It's got to constantly maintain its altitude because of atmospheric drag reduces its orbital altitude, and of course it's got to maintain its orientation in relation to the Earth, in relation to the Sun, and so on. If something goes wrong with any of that, it's a major problem. A Mars base, a Mars station, is actually fixed on the ground, so that's a whole area of technical issues you don't have to worry about. But because of these, you'll need a very different medical support philosophy to either what we do in low Earth orbit currently and for lunar missions. So we need to sort of think about things in a Martian context, not just in a lunar orbit or a lunar surface or an Earth orbit context. So just some quick ideas here in the interest of time. Habitat design. Again, one of Carter Emmett's artworks of a Mars habitat set up for a long term on the surface of Mars. You know, fresh vegetables growing there, hanging up to dry. We need to think about their food and nutrition. We need to think about medical and psychological and sociological support of an isolated crew, a small crew with limited communications for long periods, 360 to 540 days of Mars, perhaps longer if they have to, if something happens. People talk often about the stresses of that, but I can say in my own Mars simulation experiences where we had good communications with mission control, it was actually often more stressful than when we're working in areas with minimal, you know, like once daily contact with mission support. So isolation is not always a negative thing. And how are you going to manage both emergency and routine health issues in this environment? And I always remember the alleged astronaut quote about how the last flight surgeon would be strangled by the guts of the last flight psychologist, given the chance. All right, pressurized vehicles. If you're going to explore to 100 kilometers outside or away from your Mars station, you're going to be talking about using pressurized vehicles. If you're on the surface of Mars for 360 to 540 days, you've got the capability, which may or may not be realized, for spending scores of, much of your time, scores of excursions, sorties in these pressurized vehicles. How are we going to manage emergency responses, maintaining health and so on, in vehicles with limited facilities away from the station for 1 to 2 weeks at a time, perhaps 100 kilometers away? It's quite a different type of operation than what we've done before. And lastly, EVAs. Best way to explore the surface is on foot, and you know, roughly perhaps 3 EVAs a week, perhaps more, 2 per person perhaps. Comes up to hundreds of EVAs during a Mars surface stage. We've just not got our heads around what that means from a practical point of view, a medical point of view, a logistic point of view. We certainly need better suits, mechanical counter-pressure suits perhaps. We need to really cut down the time taken to depressurize the astronauts going outside, minimize pre-breathe. And this may mean we need to think more seriously, from my view as an explorationist, different atmospheres of what's on the ISS, perhaps different gas mixtures, lower pressures, or perhaps having one type of pressurization, oxygen, for example, at Apollo pressures in the rovers, and perhaps a more ISS pressurization in the habitat. And of course, again, how do we deal with emergency responses to astronauts in trouble, working from a vehicle hundreds of kilometers away from the station, perhaps a day's drive or even several days' drive?
Wonderful.
Okay.
Thank you so much, John. Look, that was very informative. Now, just a quick reminder for all the participants who are here this afternoon. Before we move along to the next segment, if you've got any questions or any items that you'd like to discuss, or just general questions, or maybe some of the panelists' specific questions, just put them in the chat box there, which you'll see at the bottom of your Zoom window, and we'll get onto those when we've gone through the next 2 segments. Now, what we'll move on to now is 2 panelists who are going to talk about real-life live simulations of an off-planet life. And simulations are very important as they teach us how to live away from the Earth, and how to handle emergencies, and how to structure our productive working life. So the first one we'll have a talk to is Dr. Michaela Mussilova, who's the Director for High Seas, which is the International Moon Base Alliance. Now, Dr. Michaela is an astrobiologist. She's got a focus on life at the extreme edges of environments. She has a PhD from the University of Bristol, some fantastic and amazing qualifications from universities and colleges all around the rest of the world. She's space research experience includes working at the NASA Jet Propulsion Laboratory, the University of London Observatory, and of course the famous Canada-France Hawaii telescope. And also she's an analog astronaut, and she's been the commander of numerous simulated missions to the Moon and Mars at high seas, which she'll probably talk about, stationed in Hawaii, and the Mars Desert Research Station, or MDRS, in Utah. She's a visiting professor of Slovak University of Technology. She's the vice chair of the Slovak Organization for Space Activities. And she's received numerous prizes and grants, including the Emerging Space Leaders Grant from the International Astronautical Federation 2016. And she's also been voted, selected one of the most promising under 30 by Forbes Slovakia as well for her efforts. So we'll hand over to Dr. Michaela and look forward to her session.
All right, well, thank you so much for a great introduction. Hello, everyone, or aloha here from Hawaii. It is Sunday here, so I'm talking to you from the past, I guess. So let me move on straight to my presentation for the sake of time. I hope this works. Please let me know if there'll be any issues. Sometimes it doesn't like to transition to the presentation mode.
You can see it now, great.
All right, is it now full screen?
Absolutely.
Okay, excellent. All right, so this, what you see in the picture is the high sea station on the volcano Mauna Loa in Hawaii. It's this little white dome with adjacent buildings. It's about approximately 2,500 meters high up. And opposite, you can see another volcano called Mauna Kea, which has world famous observatories. And yeah, this facility was originally created in a collaboration between NASA and the University of Hawaii, but it actually belongs to the International Moon Base Alliance. And those initial missions, there we go, were all long duration missions, first focusing on food. What is the right kind of food to provide astronauts with for long duration missions? Whether, we already give them pre-packaged meals, or they can use their creativity to design meals themselves with just ingredients. And after the success of that study, they started focusing on the psychological aspect of crew cohesion. So how do crew members interact during long duration missions? How to make the teamwork be more effective, people work together better, and how to deal with all the problems that will inevitably happen because humans living together for long periods of time, such a small space, will, eventually not get along. We'll have some differences of mind, so how to deal with that. These missions were very successful. Here's just a quick overview of the different ones that happened. I was actually selected for mission number 6, which unfortunately was not 8 months long as it should have been, but that's a story for another time. Feel free to ask me about that separately. Yeah, so there was a lot of information about these missions all over the media, the nutshell version of basically how to keep astronauts from going crazy on long duration missions. And all of these missions were focused primarily on Mars. And it got so famous, even President Obama tweeted about the 12-month mission that successfully happened here a few years ago. Since I became director, it's been my goal to open up this facility to both doing Moon and Mars missions, and therefore they don't have to be for many months up to a year long, but actually can just be for several weeks, depending on the needs of the researchers. I also wanted it to be open to other organizations beyond just the University of Hawaii and NASA. So we've had collaborations with different space agencies like the European Space Agency, but also independent organizations like, for example, Sensoria, whose efforts are to include more women in space exploration and people who are non-binary or who identify themselves as non-binary, and research institutions. We had a collaboration of 3 Canadian universities that came to do research at high seas. So my presentation is going to be a little bit of an overview of the different work and research we do at high seas and some lessons learned, which hopefully may be useful for the topic of how to live on the Moon and Mars and the space health part. So to give you an overview what the station is like, this is what it looks like on the inside. It's a panoramic picture, so it makes it look bigger than it really is. The station is only 12 meters in diameter. Most of the space is our shared quarters, as you can see in the picture. So imagine the same area where you're working on your laptop, doing some important research work. There's going to be someone behind you doing jumping jacks, sweating. You can smell it, you can hear it. And right next to them, someone's going to be cooking and playing music while in the dining room and so on. So it's an area you just have to learn to live with the noise, the constant interactions between the crew members. And the only places that are really private are bathrooms and your bedrooms. You can look in the picture on the top right, that's me for scale. That was what was meant to be the 8-month mission. So you can see it was pretty crammed with all my stuff. And even these little rooms don't provide as much privacy as we would like. But if you need to have some time alone, that's really where people generally go. In terms of food, people who have experience with analog missions will know what I'm talking about. Most of it is either in the forms of freeze-dried granules. I joke it's kind of like dog food granules. If you look at the pictures on the right, there's darker granules or beef, the lighter ones are chicken. I joke that color is the main difference, but if you have a good cook on the crew, they can make even these not so tasty things become something actually very earth-like. But yeah, if it's not in the form of granules and it's in the form of powder, and if you're very unlucky and you don't have good cooks on the mission, it turns into this mush you can see in the picture in the middle, and food becomes something you have to do. You have to eat it just to have some energy, but it brings you no joy. And trust me, for long duration missions, that is a big problem. Water is another thing that's very restricted on our missions and very precious. You can see there's a bucket in the picture because everyone takes bucket showers since you're only allowed to have 7 minutes of shower time per week. Some crew members like to save it up and only take a shower, say maybe once or twice a week, and then they have extra shower minutes. Others feel the need to shower every day, so it's very much up to the crew members, but it's important to save the water. However, we had instances where there was a water leak or some kind of other problem, and we were not able to use as much water as we would like to. So people had to sacrifice their showers and things like that. We even had instances of people playing poker for shower seconds. That's how important showers can be for some crew members, just to give you an idea. And in some instances, we also had to monitor just how much water we're drinking and things like that. There we go. Everything is monitored from a mission control center that's on Earth. It's actually on the big island of Hawaii as well. And we have remote support volunteers all around the world that help us with mission control work and with some of the research questions the analog astronauts may have during the missions. When I'm not on the crew, I'm usually sitting in mission control, like you can see me in the top left picture. And in mission control, so we have access to all the systems in the habitat. So we know how much water is left, how their power is doing. The power is supplied by solar panels. So crews, again, have to be very careful with the power usage because while some power is stored in batteries, if you have multiple bad weather days in a row, you're running on low power, you have to kind of sacrifice what instruments to run and what not to run. We communicate with people on mission. If it's a moon mission, there's only a several second delay. With Mars missions, can be up to 20 minutes each way. So again, that's where it becomes really important for the analog astronauts to figure out what they want to ask mission control, because they know it's going to take at least 40 minutes to get an answer, even in an emergency situation. And sorry, so just a recap, yeah, with each celestial body, let's say, that the missions are taking place on, there's a different time delay. And it also has implications for how the missions are run. If you have Mars missions with these longer time delays, the crew has to learn to be independent because, again, even if someone injures themselves, help will be at least 40 minutes away in the form of an email. Of course, if it was an emergency, then we'd have to break simulation, but that's a whole other story. So whereas moon missions, the astronauts are more in touch with Earth and therefore also more observed, let's say, by people in mission control. And so that has an effect on the way the crew behaves and feels about the mission as well. So one of the things, and that was actually very relevant this year with the COVID pandemic, is to keep the astronauts, quote unquote, sane or not bored. Their schedule is packed the whole time, like astronauts on the ISS. Basically, if you're investing so much money into people being in space, or in this case on the moon or Mars, you want to make sure you get the most out of it. But also it's a way to stop them from being bored. So from morning to evening, you have busy research schedules. There are cleaning, chore duties. You can see in the picture on the left. You have exercises you need to do. on the top right picture. And again, we have a research lab in the facility where researchers can do everything from genetics work to geology and other things. Then we have to report to mission control every day, every night. There's a time window when we communicate with mission control. People have to write reports about the research they did during the day, get approval for what they want to be doing the next day. If there's a medic on the crew, they will be reporting about the crew's health status and things like that. Just a picture, even as me as commander of missions, I still have to write reports too. On that note, I've been on over 20 analog missions now, so this place has become a bit of a second home for me. And briefly about the different research we do at high seas, a lot of it revolves around the geology of the surroundings because we are on a volcano, an active volcano. There are amazing lava tubes you can find everywhere around us. For example, if you look on the picture on the top left, you see me for scale standing above a lava tube entrance of these huge caves underground, which could serve as potential habitats. If you look on the picture on the bottom right, you can see some colleagues for scale. Some of these cave chambers are big enough to actually build a habitat inside. So space architects have been studying these as possible lunar habitats where essentially the earth, the ground is providing natural protection from radiation, for example, and micrometeorite bombardment. But these caves are also interesting from an astrobiology perspective because we found different types of life forms in these caves, mostly microbial. You can see examples of some samples we're taking in the other two pictures. And we're trying to find out how much of this is biological or just geochemical. And again, if we were to ever find something similar in lava tubes on Mars, it would help us identify if it's of biological origin or not. So these types of research projects tend to be the main focus of the different types of missions we have. For example, we have collaborations with NASA Goddard just on this astrobiology aspect. Other missions focus on space architecture and things like that. Then most of the missions are accompanied by psychological, physiological, and basically sociological research on the crew members themselves. You can see some examples of what different kind of exercises we had to do. So if you look on the pictures on the left, you can see we're all wearing these so-called mood sweaters, different colored sweaters around our necks. And they were meant to show how we're feeling. And it's meant to increase empathy between crew members so we can work better as a team. And the picture on the left and the bottom, basically we're doing an exercise where we have to turn over a tiny carpet that we're all standing on while still standing on the carpet. You probably might be familiar with that exercise, except it was a really tiny carpet and we had to do some gymnastics to make it work. And as you can see, all our colors are blue. That means we're very focused. But then they also look at how our physical state changed over the duration of the mission, whether exercise helped the crew or actually just made it even more difficult for us to be on mission. And then since we're at the Space Health Symposium, I had to mention some medical related exercises we did. So here's a mission where we had a doctor on the crew and together we prepared a medical evacuation exercise. So here's the doctor giving the briefing. He and I organized it and I was in on it. I was going to be the victim. It was pre-planned. And so basically we went out on EVA and suddenly I collapsed. I supposedly had some hemorrhaging in my leg and I also hit my head. So I was becoming delusional. I'm no Oscar actress by any means, but I definitely made it very difficult for my colleagues to take care of me. So here you can see in the picture, they actually very cleverly used our knee pads as a way to block the blood from essentially escaping from my leg. So that was a very ingenious way of sorting out, the situation with the few things you have with you in the field. Then other crew members went to get help from the habitat. The whole crew left the habitat with this blue board you may see underneath me in the picture to help carry me back to the base. They also took care of my other injuries, and then they had to find a way to secure me, so they actually had to duct tape me to this board to be able to carry me. And then it was basically 4 ladies that carried me for normally a distance that would take maybe 5-10 minutes to walk. It took them about 40 minutes to get me back to the hab, because again, with all the EVA equipment, you're a much heavier person. and the board was heavy too. So you can see that they had to traverse the difficult lava terrain. And when they got close to the habitat, it's on a bit of a hill, so they had to push me uphill. It got so difficult that they had to get this little trolley thing, put the board with me on it, and they were trying really hard to push me, but yeah, it was a lot of effort. So again, it was a great exercise to see what to do if something like this happens in the field, how long you can remain in simulation instead of having to break simulation and, you know, call for help from Earth. And of course, what would happen if you were really on the moon or Mars? How would you deal with the situation? Would the person even survive by the time you got back to the base? So we do different types of exercises like this during our missions. Other human-related research we do is, for example, space architects covered our whole habitat in white, and they were trying to see what the lack of color, how it would influence the crew members. And only a week of that, and some people started to go a little bit crazy. They literally tore down the white paper. You can see them putting up on the walls when that week was over. So even little things like color can have a big influence on how crew members are getting along during the mission. And then, computer's being a bit slow. Let's see, did it freeze? There we go. The other kind of research we do is also focused on technology. So we test different types of potential analog rovers and drones. Some rovers are human-sized, which previously it was a collaboration with NASA, but it's a Hawaiian organization called Pisces that takes care of that rover. And because we do so much engineering work, we have to have at least one engineer on the crew. You can see different crew members from different missions doing various types of engineering work and maintenance during the missions. Again, they're in charge of our life support system, so they're very important crew members, and they do have their hands full trying to take care of us. And then we do a lot of educational and outreach activities to tell the public, you know, why it's important that we practice all of this, what are the lessons learned, and how we can apply some of this even nowadays during times when people have to be in quarantine or lockdown. What have we learned that they could apply to their daily lives, which is something I was doing a lot this year. Even recently, this documentary, Space Drop, came out, and it was essentially how to space quarantine. And the picture on the top and the bottom right, you can see me with my hair and an obscure looking liquid in my other hand. That's actually broken down hair into this liquid, which was meant to be used as fertilizer. We were able to grow spinach out of this, and it was part of a high school project that students designed for our mission. It was very successful. So we're always happy to have young people involved in our projects like this as well. And ultimately, we hope to collect all this data, these information from our different missions to help people be able to actually build a moon base on the moon or one day go to Mars as well. There's also a possibility to get involved in our missions through mission support in various ways. Please let me know if you would be interested in that. We're always looking for volunteers. And here are my contact details if you would like to get in touch. We are regularly recruiting for crew members, but also research projects to be involved in our missions. So I'll be happy to discuss this more with you. Thank you. Thank you very much for your attention.
Thank you so much, Michaela. That was very informative. And once again, please, anybody got any questions of they'd like to just chat about afterwards? Just for the sake of time, we might just keep rolling forward pretty quickly to our next presenter, Guy Murphy. Guy is also a director and member of the Mars Society, but not just that, he's also one of the founders of the Mars Society in Australia. And he developed an interest in science fiction, and sort of that kicked on his fascination with Mars particularly. He's been involved in Mars simulation missions, along the lines we've talked about, and he's a graduate of University of Melbourne. He's a researcher, writer and historian based in Melbourne. So hopefully he's surviving the lockdowns okay then at the moment. He's co-authored a number of papers, and as well, he's an author of a book called Mars, A Survival Guide, which has been published by HarperCollins. So Guy, like to have a chat to us. We look forward to it.
I was fascinated to hear Michaela's talk, which gave a good overview of one of the major space analog research stations in the world, one of the significant ones. And it complements my talk today, which is about an expedition to another facility, the Mars Desert Research Station in Utah. And the Mars Desert Research Station is run by the Mars Society, and it was established in the early 2000s. Just to take a little step back to help you understand the components of the station, I'm going to just return to an image by Carter Emmert from the series John Clarke previously showed. This is a fictionalized imagining of an early Mars first landing base. And it's particularly useful for our purposes because it shows in quite a rigorous way the various components you typically have. So you see here in the center, there's some landing units that contain habitat living spaces and working areas. You've got greenhouses in the foreground for growing food. You've got systems for producing energy in the background, solar arrays in this case, various sort of life support plants, perhaps chemical processing facilities. You've got vehicles around the base, and you've got an airlock device area on the left. That one's got quite a large one with a vehicle. And you've got communication antennas, so communication facilities for keeping in touch with home and with other components of the mission. So thinking about that, the Mars Desert Research Station is a simulation of that kind of first landing post that has many of the common elements you would typically see. So there's a central main habitat, which is referred to sometimes as the tunican, which has got living spaces upstairs, working areas downstairs. This image shows the MDRS as it was first built in 2002. It's since evolved, but if you look at it, you'll see, thinking of those components I spoke of before, there's a small greenhouse on the right. Out of sight, there's actually a generator power source around the corner. You've got aerials and satellite dishes for communications. You've got vehicles. There's an observatory here. So Expedition Boomerang, which is going to be the main focus of my talk, occurred in the context for me of a 17-year involvement in this place. I first came to the Mars Desert Research Station in 2003 as part of Expedition 1, which was a joint Australian-Canadian mission. And I'm going to just briefly mention this just to give you an idea about how you can vary missions at one facility, some of the ways in which you can vary them. This was a very large crew. It had a total of 30 people involved, with an average of 11 there at any time in week-long cycles. It was running partial simulation for the first 3 weeks with full simulation towards the end. It was quite a young international crew with a very diverse, varied range of skills and expertise that were sort of contributing to the mission. And you see there Shannon Rupert, who is now the director of the Mars Desert Research Station. So that's a big crew, a big young crew doing with a particular focus. And these are just some random pictures from that expedition. We had simulated rovers on it that were doing things. So this was kind of a mega mission, but it was quite early in the history of the Mars Desert Research Station. The missions there were organized in two-week rotations. So you have rotation 1, rotation 2, so on. This was rotation 14 at the start. So it's very early on, and the facility just been started quite well, it was only a few years old, and a lot of ideas were being developed about how to run it, and people were starting to imagine what facilities they'd really like to have there. Fast forward now to 2019, crew 214. So this is 200 crew rotations later. So that's many years of different crews coming, trying different ideas, procedures being refined, but also physical evolution of the campus occurring. So from that small facility I showed you in 2003, the campus has since evolved to a bigger complex of buildings. You've got a larger greenhouse. You've got the Science Dome there, which has quite extensive facilities inside. An engineering unit there on the left. The observatories moved from the hill down to here. These are connected by notional pressurized tunnels. They're not actually pressurized in real life. This is not a highly engineered sort of flight ready sort of mission hardware you're looking at, but it aims to replicate the kinds of living spaces and constraints that people undertaking a Mars mission would experience to sufficient fidelity where people can start to do some serious research here. Out of sight is a solar array, so there's an energy source, and there's communications and so on, and vehicles. So it's become more elaborate and sophisticated since then. So John Clarke was on Expedition 1 too, who you've heard speak today. So introducing the crew of Expedition Boomerang. It comprised 2 crew rotations of a fortnight each, and that's our crew. Sandy Dance, he's a computer scientist. There's Shane Usher, who will speak a bit later today, engineer. Geologist extraordinaire and Commander Andrew Wheeler. There's Diane McGrath, who's a Mars One candidate and is finishing PhD on looking at food waste. Steve Whitfield, who's a paramedic and lecturer in Queensland. Larissa Wilson, who is a final year engineering student from the University of Canterbury, New Zealand. We have Jennifer Lane, who's undertaking a PhD looking at Martian habitat design, so it's architecture. And myself, who's, as per my introduction, a long-term Mars Society volunteer, but also I work in architecture in my day job. So this was a bit different from Expedition 1 in that we had, for the first crew rotation, we actually went down to 4 crew members. We had someone who was unfortunately ill and couldn't come, and but crew size and composition is one of the things you can look at in simulation missions. So that was a really fascinating thing, seeing how the different crew sizes worked and what the dynamics were. We did operate in a full simulation mode for each of the 2-week rotations, and that was broken for the swap over between rotations and at the very start and at the very finish. And the crew brought together a whole lot of sort of diverse fields of expertise and brought research projects associated with those. And one of the requirements that the MDRS management has for incoming crews is that you allocate particular roles to crew members. So there's a crew commander who sort of oversees the overall mission, manages the crew where necessary. There's a crew engineer, because the crew, someone in the crew needs to operate and maintain the living systems, including like water and power and so on. Not so much power, but just the life support, what we regard as life support for the mission. There's a medical officer, a green hab officer, a journalist to write daily reports to communicate to the outside world what's going on. And then there might be duplicates of people in the same roles, or specialist researchers. So I'll just quickly skip through to what some of our major projects were. A micrometeorite collection project. That was quite critical because one of the things crews must do is organise some serious activities that involve going outside in simulated space walks. And our micrometeorite collection project, which we did on behalf of Dr. David Cooper, who wasn't able to come on the mission, gave us a useful task to do on EVAs over the course of the mission. So there were different projects that people brought. And there's obviously also housekeeping as well that needed to occur. Now, if I just hone in on EVAs, which is, if we're going to send people, John Clarke touched upon this and you also saw it in Michaela's presentation, if we're going to send humans to Mars on long duration missions, they're going to need to be going outside for various activities, and not just once or twice, just routinely over a period of years. So we need to, there's a lot we need to perfect about how to do that safely, or come as close as perfecting. It will always be a dangerous activity. And there's also a lot of different aspects to investigating how to successfully do EVAs. The MDRS has two different types of spacesuits that people wear when they go outside on EVAs. You see here, the top left has a separate helmet. The bottom left has a built-in helmet. And there's a set procedures for people going outside. They need to book in a time with mission control, have a particular reason for going outside, and then put on their suits correctly, then go into an airlock and have a notional depressurization. And then once outside, undertake whatever it is that they've been assigned to do, whether it's maintenance around the habitat unit, the campus, or going further afield in vehicles, which we have, which you see top right. In the bottom there in the center, you have a picture of me out doing the micrometeorite, some of the micrometeorite sample collection, which is in using a magnet. And there were 2 sites we went through and looked over the period of a month and collected samples for return to Australia and examination. And when crews go out, they need to be supported by radio, which you see me doing up right. Now, if you look at the mission reports for the various Mars Desert Research Station crews, you see extraordinary imagery. The location where the Mars Desert Research Station is set is a really extraordinary place. When I didn't realize that the cartoon Roadrunner is set at a real place. This is southern Utah, minus the cactuses. It's really weird. It's to Australian eyes. There's no green at all. That's quite odd, having a bit of dead vegetation in the background. Very strange alien landscapes, quite unlike anything that I've seen in Australia. And you can really imagine that you're in an alien world when you go out. Particularly when you're wearing spacesuits, it's silent except your radio. It's quite extraordinary. And it's really, that's a really overwhelmingly powerful aspect of this place that gets you in the zone, makes you feel that you really are on Mars. And the nature of the habitat and the campus architecture also helps get you there. But it is a very extraordinary, visually stunning place. So I mentioned, there's been mention of food already, and every time I go on the expedition, I'm once again reminded how central food is to the success of any expedition. There's on long duration Mars missions, any Mars mission will necessarily have to have food that can be stored for a long time, preferably dehydrated so it doesn't minimize the weight. And there's similar dehydrated food as what you saw at high seas at the MDRS. And on the face of it, it would not seem particularly appetizing, particularly to Australian eyes. We're not used to tinned vegetables and tinned meat, but actually you get very inventive and creative and learn to do things with it. And we continually surprised each other and stretched our creativity with what we're able to come up with. Yes, there are croissants in the bottom right. Larissa, who was with us, was an extraordinary cook. There's just some people at work. I won't talk about projects that other people did. They're best to present, talk about their work better able to than I am. But Andrew was looking at water extraction from minerals. Diane there in the middle was looking at food waste. And Steve Whitfield at right, you can see, was looking at field emergencies in the Mars simulation context, and we ran a number of simulated emergencies to see how we would respond. Shane was looking at engineering systems, and he can talk about that better than I'm able to. I was Green Hab officer, which I have background in horticulture. There's the Green Hab top left. we were the first missions for the season, so there was very little growing when we first got there. So I basically potted everything up and planted crops. There was a lot of seeds. So that was part of what I did. It's potting around plants is very therapeutic. People in the International Space Station love nesting around the greenhouse. I did notice the lack of fresh green leafy things. This greenhouse does produce output that gets eaten by the crew later in the mission. It was very rewarding to see that happening, observing subsequent crews. I'm running short of time now, so I better kind of wrap things up a bit. I think it was quite an extraordinary mission for all involved. And a number of studies were completed, and we'd love to go back there again when the COVID situation eases. And it's been really interesting to see how the facilities evolved over time. It's just got a lot more sophisticated, and it's really proved to be something that's very valuable. It was really innovative and regarded as quite out there when it started up, but it's made a very serious contribution. And you can read more at that URL. So thank you, everyone.
Thank you so much for that, Guy. That's an amazing journey. One thing I will ask, and just a quick question to Michaela, is you mentioned that there were some issues with simulated rescues. In your experience, have there ever actually been any real emergencies that needed attending to?
Yes, so unfortunately, yes, I have been part of missions where we did have some real medical incidents. Luckily, for the most part, it's all minor stuff, bruises, scratches, whatever things we can kind of deal with the equipment we have, or you know, the first aid kits we have on the spot. Sometimes when it's more serious, but we can still keep simulation, for example, a cut, we communicate with our on-call doctor who walks the medical officer of the crew through how to dealing with the cut or whatever the medical issue is. But when things get worse than that, that's when we actually have to break simulation. So we had one instance where we actually had to call paramedics to get someone. And nowadays, the emergency services know exactly where we're located. There's a military base, only say 40-minute drive from the station, so they were able to get to us pretty quickly. And there's a possibility for helicopters to come and evacuate someone if necessary. Luckily, that has never been needed. Yeah, we anticipate problems can occur for various reasons on missions, including that the lava terrain is pretty risky to walk on. So that's why we have the crews go through thorough training before they even start the mission, or sometimes they have to do the training in the mission, like now during quarantine times, but they won't go on EVAs until they're ready.
Thanks for that. Well, let's move on to the second lot of panelists, and we'll do a similar thing. First of all, we'll just have a talk to Dr. James Kurrle from, he'll be talking about life and living outside the Earth's atmosphere. We've got two more speakers as well, and we'll also have a bit more of a panel discussion from there as well. So James, over to you.
Thank you. Okay, so initially, thanks for inviting me to talk about this. Sorry, worst angle for this camera right now. I've got nothing to really disclose, no financial relationships or any concerns. So I'm actually going to cover some of the things that we've already covered in some ways. So I'm going to brush past some bits, but I'm going to get through the denser stuff at the start. So one second, I just need to move this out of the way. So essentially, I'm going to talk about bridging the divide between medical and engineering teaching. We've been, for the last couple of years, we've been doing basically these simulations at the MDRS where we take 7 doctors and we go through basically a simulation, talk about a lot of the medical sides of things and how we can, better engineer things. So we basically are teaching medical people engineering stuff. Recently, we changed it over and did the actual opposite. So we started teaching some engineering students about medical stuff to try and bring the divide closer. We'll go through. So basically, this is the overview of what we're going to go through. I'm going to click through because if we do this in a decent period of time, there's a video. Okay, so initial question is, why is it important to bring space and medicine and engineering together? This is actually touched on before by Daniel in one of the earlier presentations. So collaboration leads to better design. You know, if you can understand what the doctors want and what the engineers can provide, that's going to increase our chance of getting what we need for the situation and provide healthcare in better ways. Understanding those engineering constraints is definitely a difficult thing for some doctors who just believe, you know, these things can just be fixed. We can just add another thing to it, bring another piece of equipment up with us. But the problem is we don't always understand that, you know, there's only a certain finite amount of resource we can bring to these places. And, you know, how many of these things could we actually bring before it becomes a useless endeavor? So it's an interesting viewpoint in medicine. It can provide a better understanding of healthcare and physiology when looking at the engineering side of space medicine. Second question is, what can we learn from these analog missions? So wilderness medicine encounters a lot of the same issues that will occur outside the terrestrial environment. Things like difficult access to healthcare, limited equipment, environmental extremes, both hot and cold, which is what we did experience on the MDRS, operational performance and improvisation and innovation, finding what we've got and trying to fix the issue as best we can. Simulating these situations increases the chance we'll already be ready when these medical emergencies do eventuate in space and off-world, because we've seen these things before. As seen in Guy's talk and Michaela's talk, there are these simulations we can do, and we can actually learn how do we fix this little problem that we wouldn't initially think of, but later on we have issues with. For example, in MDRS, we'll go through a little bit of the structure in a second, but getting someone in the airlock in a gurney is actually incredibly difficult. It's not a simple, just throw them in there, it's fine. Sometimes the gurney won't fit. I digress. The third main question was, why do analog environment missions rather than just teach purely in classrooms? Learning is definitely stronger when you apply what you've learned to an actual and real environment, an actual situation, somewhere you can think back and be like, that's when that guy fell over and then we did this to splint his leg. You can always workshop these things, but in the end, it comes down to if you've seen this happen and you know what you're doing and you've seen it happen, you're much better off. Space and off-world life will have foreseen and unforeseen issues, and these missions expand our knowledge about some of these unknown unknowns, as in the things we don't know that we don't know. Also, it's fun to go to adult space camp. All right, so I'm going to skip through a bit of this because we definitely have covered a bit of the MDRS already. Long story short, it's in the middle of Utah. It's a Mars Society project. It's a laboratory for working out how can we live and work on another planet. There's a lot of people and been plenty of crews. I think it was 221 or something he said in the last presentation. It's an interesting environment. There's limited consumables, water is trucked in from town intermittently, there's non-perishable foods, there's a solar powered backup generator, the internet's sporadic, there's a lot of constraints we've got. If you want to know exactly where it is, it's sort of that southern part of Utah there, and you can see on the Google Maps image on the right that it is a pretty desolate area. There's really not much, and Hanksville in the middle of that is really not exactly a big town. So we've gone through this. I won't explain any further. We've covered this a couple times now. Here's the floor plan. So you can see on the left is the ground floor and the right is the top floor. For those that have been there before, they'll already know exactly where these things are, but the main things to note for us is that the EVA airlock on the right side is sort of the middle of the image there, and the engineering airlock on the other side, where there's a nice big open area on the bottom end with a shower and toilet at the south end of it. Then upstairs you have 6 beds in sort of bunk formation, but separate rooms. And then the other hemicircle of the room is the kitchen and sort of living areas. The Wilderness Medicine Society is a group of people that they're a leading organization on wilderness medicine. They focus on all these pre-hospital, middle of nowhere, how do you fix someone who's fallen down a mountain and needs this fixed up? There is various areas inside that, including there are first responders, combat support medical personnel, nurses, physicians, paramedics, helicopter retrieval people. There's lots of people that are involved in this. They do a lot of different things trying to advance healthcare in these situations, including research and education. And some of the things they do is something like this. So they are more than willing to start having these expeditions, basically. So they do various mountains and climbs and places around the world where you can go and visit and learn about wilderness medicine at the same time. And with these people, one of my friends, Ben Easter, sort of developed amongst 4 other doctors, including a NASA flight surgeon, this program basically targeted physicians and medical care providers, so physician assistants and nurses can come as well, with interest in space medicine or healthcare in remote environments in any way. It's not the cheapest. It's $2,700 US for 1 week, inclusive of virtually everything except for getting there and getting back. But what makes it very attractive for doctors and why we've got such a long waiting list for it is that they get 37 of their medical education points. We have to, every 2-year period in America, you have to accrue 50 units. And 37 units is most of your way there. So it does speed things along. We do have some involvement in research initiatives. So we do some sort of just-in-time training with ultrasound and some other things like that, but it's optional for the participants. They get small private rooms with shared areas, again, austere area, and do a lot of bouldering and sort of that sort of thing. So they need moderate fitness equipment. This is the actual site, the Wilderness Medicine Society, for the course we're talking about. I'm talking about 2 different courses. This one's just for doctors or for physician people or medical people. So the days broadly consist of lectures in the morning, so about 3 hours of lectures, followed by EVAs in the afternoon. Each of the EVAs, we insert some sort of medical emergency or other medical situation that would be of use and something we could look into that might be important to know more further about. And at the end of it, we then go through all this stuff and cover what was good, what was bad, what could we do better for next time. So they're all in the local area using all-terrain vehicles. This is actually in I think it's called Ice Cream Valley or something like that. And I will totally tell you that I did soup up the colors. They don't always look like this. The team works together in these EVAs to complete the scenario. The roles assigned. They do a lot of their communication over short range radio. Some examples of the EVAs we've done is search and rescue, where I was part of the Australian contingent that crash landed on Mars and they had to come and rescue us. I was hypoxic with decompression illness because my suit had torn, and my compatriot Australian friend was had a head injury after falling into a ravine. Another one was a solar particle event where we had to basically choose whether or not we would go and warn the other group that's a bit too far away for us to have immediate radio contact, or just let them go because we're going to save ourselves versus try to save more people. So it was a good ethical dilemma. We went through some medical events in the field, but also inside the hab. And we also did a rocket launch. We have this anesthesiologist friend that comes down for a couple of days, usually each time, and launches a solid state rocket. Last time we did it was 18,000 feet. It was pretty interesting. I've got some pictures of all that stuff. You can see on the top left is the ATVs. On the right, there is actually me being the dead body, or actually no, that's when I was hypoxic with decompression illness. Bottom left, there was a fire inside the hab. So we set up a smoke machine and this sort of fake fire, which was really just an orange lamp, but we tried to make it at least as reasonably fidelity as possible. Here's a quick little video just to see us going along. It's only a couple seconds. It's a lot of fun playing around with this stuff, Should not that you need to have a bit of training on it, but still. That brings us to the second part of the course. So this other course we added we've only done once now. So that same Ben Easter and the group of us sort of became, he was already at the Department of Emergency Medicine at Anschutz in Colorado. So he ended up getting in contact with one of the engineering professors. And between the two of them, they've decided to put this course together. So long story short, Colorado University has been doing a lot of stuff in space for many, many years. They've got many alumni have gone to space, the most recent being Chell. They do a lot of they get a lot of funding from NASA, but they also get a lot of funding from elsewhere, and they devote a lot to space research. So as I mentioned, the collaboration between CU Anschutz and CU Boulder, the idea was to expand the medical to Mars program, which is what we were talking about before, and adapt it for aerospace engineering students. So the first iteration was 2019. There was an intensive summer course with a week of dense lectures covering a lot of medical topics. These are people that had virtually had no experience of medicine. We focused a lot on wilderness medicine, and we actually had them, if they wanted to, they could sit an exam at the end to get accreditation with the Wilderness First Aid with the Wilderness Medical Society. So they did a week of lectures and then came out to the field for a week. There was about 20 students. They were camping in a hab rather than accommodated inside the hab, and accommodated by an exam, as I mentioned. But they also, when they returned back to Boulder, they had to present a medical viva. And what that means is you basically have a scenario ahead of time that they could prepare for, and they could bring in 1 page of notes, but they basically had to explain how they would fix this situation in space. And one of them was a person with a renal stone, and that's a very particular situation. They have to work out if would it be worth bringing an ultrasound or not bringing an ultrasound? You know, how could we fix this on site? You know, what would you say to Houston, which is what the last thing they had to do was basically radio Houston and say, this is my plan, this is what I want to do, let me know if there's anything you need me to do. There was actually 2 people that were incredible. Like, I have not seen doctors do as well as that. I think we've got enough time, so I'm going to hit this video.
A human mission to Mars is no longer a dream. It's a reality driven by mankind's search for answers, our quest to find cures and solutions in outer space to the biggest challenges we face on Earth. Dr. Benjamin Easter of CU Anschutz and Dr. Allison Anderson of CU Boulder are leading a team of innovators to further a new frontier: medicine in space and extreme surface environments. Their team is powered by some of the nation's foremost experts in aerospace engineering and extreme environment medicine. Our first-of-its-kind program in the country is training doctors and engineers to address human medical crises in space and the utterly remote, unforgiving environments on Earth where there is no margin for error. Because we must be prepared to handle the infinite problems that can arise when help is 6 months and 250 million miles away. University of Colorado Anschutz Medical Campus and the University of Colorado Boulder, we are developing the first responders in space. We are not just exploring the possibility of a better future on Earth and beyond. We are creating it.
All right, you get the point. So that's where they were camping. The actual MDRS is sort of around the corner here. You can't see it where they are. Obviously, we went out in all weather. Sometimes the weather got pretty bad. Unfortunately, we were really hoping for some good weather for the rocket launch, and luckily it happened on the second last day. But otherwise, we couldn't have launched in this, unfortunately. All right, so the difference between the 2 courses and the biggest things we learned from it, there's a significant increased participant size changes a lot of things. So as someone mentioned before, that when they had a large crew, it does change quite a lot of factors. So the EVAs ended up being a lot more complicated. Like in the search and rescue scenario, we had a team which was inside the hab coordinating over the radio, different teams to go to different areas to search for these people, which was me and my friend. And then organize how to get them back, how to reallocate resources and things like that. Teaching medicine to engineers versus teaching engineering to medical personnel is a very different factor. Like the engineering mind, when you come to medical stuff, is a certain path, whereas medical people are understanding that there's a lot more variance to some of these things. There's nothing is as set in stone. There is, not to be like all idiosyncratic about it, but there are certain differences between how do you teach them and what you teach them. So prior lecture teaching, so because for the students, they actually, a lot of them knew each other. They had a lot more relationships, they had a lot more friendships inbuilt in it. It actually changes quite a lot of the group dynamics and the psychology of it. When you get 5 people or 7 people thrown into one area which don't know each other, they have to sort of restart from the start. Whereas these other people, they actually knew all these friends, they already had like social supports around them. Finally, engineering the projects to the engineering students had a project to create a payload for the rocket that ultimately was launched and recovered. Essentially, the idea was to have a rocket that could launch supplies from wherever they are to a point in the distance where they would need the supplies. For example, you could send, IV fluids, blood, new medications to someone off in the field that would require them. So here's just some pictures of the search and rescue. They were doing some widespread looks. This is actually the lower end of the hab. You can see when there's a lot of people, it becomes a bit of a zoo. There's 2 people having CPR at that point, and then 1 person at the back's got hypothermia. They had an in-hab fire where they had to go and find the person that was still inside without losing themselves in the smoke, because it actually was, despite what you can see there, it was actually very difficult to see around. And then also put out the fire. There's an interesting story a couple of years ago where one of the doctor participants found a real fire extinguisher and used that on the fire, which is literally an orange lamp, and ended up smoking out the whole cabin because it was all the actual old CO2 stuff. Anyway, moving on. So this is the payload design and launch they did, and that's Dr. Earl who helped out with the launch. And finally, to wrap it up, the plan for this year was to do back-to-back courses where the engineering students had already done a weekly 2.5 hour lecture up until the point that COVID really started becoming a problem. And we were going to do both a doctor mission and a engineering mission back-to-back, and I was going to be there for the 2 weeks. But unfortunately, COVID started becoming just a bit of a problem around then. And in the end, we decided it was a better part of valor not to go ahead. So we actually canceled the whole thing, unfortunately. We will return sometime when the risks are ameliorated. And that's it. Thanks so much.
Thank you so much. Thank you so much. It's fantastic. It's fantastic. We'll move straight on, if possible, just for the sake of time, for Dr. Sid Pandey, who's also a director of the Mars Society Australia, and has been involved in the study of astrobiology for a while. He's actually the head of the recently established Centre for Excellence in Astrobiology at Amity University in Mumbai. And he's setting up what is perhaps India's first dedicated Centre for Astrobiology and Space Biology research. Sid's got a long experience in sort of leading teams working in this area. He's worked at NASA Ames, amazing background. He's got a PhD in aerospace engineering from the University of New South Wales, a master's degree in space systems from the University of Delft in the Netherlands, and a Bachelor of Technology in Aerospace Engineering from Amity University in India. So having heard Sid talk on numerous occasions, he's always interesting to listen to. So I'll hand over straight to you.
Thank you so much, Earl, for that very kind introduction. I'm going to try to share my screen now. So very warm greetings to everyone. And firstly, thank you so much to Rowena and the other organizers for this opportunity to speak at the symposium. These are exciting times here in India, and I'd like to share some of the updates and some of the capabilities that we have here and offer those to the participants and the other communities that are involved. So Earl's already mentioned this. I have had the opportunity to be in Australia, work in Australia, and also in the US. So some of these functionalities are things that are really, really critical to where India is, at this particular stage. We're actually gearing up, for some very exciting things here with the Indian Space Research Organization having plans for a human spaceflight program. In fact, the next vehicle, the GSLV, which is our human vehicle that will be taking 3 Indian astronauts into orbit by 2022. So there's a strong national sentiment for space exploration. And there's going to be a test flight that will be happening sometime early next year. And then on the other side, in terms of planetary exploration, India has already embarked on orbiter missions, both to the Moon and Mars, and there will be a more elaborate surface exploration mission for the Moon by the name of Chandrayaan-3, which will be a lunar South Pole mission. And while all of these things are taking place, the other positive thing that has happened is that the Indian Space Research Organization has made serious efforts to open itself up, not just to universities and non-government players in India, but also to international collaborations. So that's the other positive thing. And in fact, just a week back, we had a conference where the Australian Space Agency was speaking at the Conference of Indian Industries. So there's a lot of, I think, positive developments for people to work together. And I will, focus my 12 minutes or so on analog research. So I don't think I need to, tell you all the importance of analog research. I think all of that has already been well established. So I would like to focus the attention of the participants towards one area in India by the name of Ladakh. So this is in the high altitudes of India. It's a similar landscape to Tibet, for those of you who are not familiar with the Ladakh region. So it's immensely important from both a science as well as technology and operations point of view. So it's a high altitude, very high altitude environment. We're talking about anything between 3,500 all the way to 5,500 meters above sea level. And that high altitude gives us low oxygen levels, high UV radiation levels. And from a scientific perspective, it's like ancient Mars. So from the Hesperian age, we're basically looking at a point of time in the history of Mars when it was warmer and had liquid water on its surface. There are several features in present Earth scenario in Ladakh that can mimic these kind of conditions. And I'll talk about the different diverse environments that it actually has and the opportunities that actually open up for researchers to conduct their experiments. And since 2016, I was the program coordinator for the NASA Spacebound India program. We partnered with Mars Society Australia, several researchers in Australia, as well as in Europe and in the US. And we conducted this first ever international astrobiology expedition to the region. And I'll be presenting very, very quickly on some of the progress that we made there. And lastly, with Ladakh, I'd like to point out is that my university is currently working towards establishing a research station there. So these are early days for us, but I would like to share, some of the highlights of the station and the things that will be happening there. So just to highlight some of the important features at Ladakh, I think what sets Ladakh apart from other Mars analog sites is the diversity of the different you can say ecosystems that exist. So within about 100-kilometer radius, you have high altitude, very high altitude passes. So about 5,500 meters above sea level, and you have these glacial meltwater pools. Here you can see two geologists collecting a core sample. In fact, Dr. Jonathan Clarke, who's on this particular panel, he was there with us. He was in fact the science coordinator for this particular expedition. And that's obviously very exciting for people who are looking at UV radiated microorganisms that are living in these fresh meltwater pools, and also looking at the topology and the morphology of that particular site. It also has sand dunes, so similar to the ones that we see on Mars. And these sand dunes also have seasonal ponds. We have a lot of clay deposits in those ponds. So it's exciting for those of us who are interested in organics on the surface of Mars, looking at the abundance of clay. And clay, as we know, is an excellent preservator of organics. And we had a team from the ExoMars Habit instrument. So Habit is an instrument that will be flying to Mars as part of the ExoMars 2022 mission. And the team was basically testing out a prototype of that instrument in Ladakh. So primarily looking at the local environment, measuring wind speeds, relative humidity, looking at how, and it was carrying a small box in which it was carrying different salt samples, and then seeing ways in which you could actually, hydrate these samples over time and testing its efficiency, because that's something that is of interest right now when we're seeing, liquid, salty, briny water on the surface of Mars. It also has, I think, something that is really, really important from an astrobiology point of view, these high altitude hot springs. So what sets aside these particular active hot spring sites is that they're at this really, really high altitude, which allows the water to in fact boil at 75 to 80 degrees Celsius, simply because the atmospheric pressure is almost half. So the water boils, and it has this unique geochemistry because of this unique environment of low temperature, low oxygen, high UV radiation. And you have these microbes, different colonies of microorganisms that are growing at several different locations. If it's a large hot spring field, you can say, and then at different points, you have different kinds of environments that are set in. So it's extremely exciting for people who are interested in understanding what ancient hot spring deposits are like on Mars, and also to communities here on Earth who are interested in the early Earth. So it's one of the hotspot site, quite literally, for teams who are interested in solving the origin of life, the terrestrial origin of life. And there's a group from Australia, in fact, Dr. Martin van Kanendonk, and now recently also Dr. Kathleen Campbell from New Zealand has also joined our research efforts. And we hope to continue doing more and more research and connecting it with some of the work that has come from Pilbara in Australia, as well as in New Zealand at the Rotorua Hot Springs. Moving on to another strong science group, people who are interested in understanding what halophiles are like. So halophiles are salt-loving bacteria, and you have these receding lakes or basins now. So over a period of time, we can actually visibly see the effect of climate change. You can actually see all of these lakes that are now slowly receding and becoming smaller and smaller and more concentrated. And alongside the shores of these lakes, you have colonies of microorganisms that are living in these really harsh and salty environments. So that's interesting also from a Mars perspective, where we're looking at these ancient, lake beds and trying to understand their potential in preserving some of the organics of potential past life on Mars. And alongside these lakes, in some locations, we also have permafrost, which is of course also very exciting. So as you can see, I'm building this entire picture for Ladakh. It's got all of these exciting features that actually cater to many different lines of research that pertain to Mars exploration. And we actually had measured permafrost in our 2016 expedition. And I'm actually traveling there next week for some more work in regards to our station. And I'll be taking more images and taking some more measurements to compare with what we had seen 4 years back. So this is just to summarize. I don't want to go into full detail, but just to summarize some of the different work that we kind of embarked on when we were there. So we divided the sites based on the region. So we had the high passes. We visited 2 different high passes. There were the sand dunes, and ponds, the hot springs, the saline lake, and the permafrost. And in terms of activities, we carried out different activities. So Dr. Jonathan Clarke, he led the regolith landform mapping technique. So this is a ingenious technique that he has come up with another colleague of his, which basically divides a particular site image and ground truths it with aerial and satellite imagery. And it's basically to help characterize all the different features in that image. And also other similar geomorphology related studies, the testing of the instrument habit. We also, in fact, did a transit study of measuring the abundance of biodiversity along the transits as we were going along. And we were measuring it using 2 different techniques, ATP and LPS. I'll not go into details, but basically, all kinds of studies that involve in situ or handheld based instrumentation that can be used to measure the microbial diversity of a particular site and seeing how it is changing based on the terrain, the altitude, or any surrounding parameters. So biomass distribution obviously being very important, and also the metabolism. So we were actually studying the rate at which the organisms inside the hot springs were actually consuming glucose and seeing how they were doing it, how well they were doing it at different hot spring temperatures, water temperatures. So moving on to another site in India, a little further away in central India. This is a crater site called Lonar. So Lonar crater happens to be one of only few other craters on our planet that are still well preserved in basalt. Basalt being a really hard form of rock. We see on Mars and other rocky bodies in our solar system, several of these kind of basalt craters. And what has become very, very exciting right now is the NASA 2020 Perseverance rover is actually headed to land inside a crater that is similar to the one that we have here in India. And it's an astrobiology mission. Its objective is to look for signs of present or past life. And the reason why it's doing that inside a crater is crater being a site where water has clearly, we can see in this image on the top right, it's got an ancient delta. It's got signs of water streams that had been flowing over time and then depositing layers and layers of sediments, and perhaps inside them any organics and proof of any biosignatures. That is exactly what the 2020 rover will be doing. And in 2019, so last year, we made 2 trips to Lunar Crater, and you see over there Dr. John Clarke on my right, Dr. Jennifer Blank from NASA Ames, and also Ms. Annalie Beatty. We were all there together it was a pathfinding expedition to the particular crater. And basically, we have drawn similarities between the 2 sites, and we are proposing it as a place where we can do a lot of crater habitability work in trying to understand ways in which you can study craters using drone-based systems, because a lot of the terrain is non-traversable inside a crater. So we've actually come up with exploration goals for Lunar Crater, we've divided the entire site into 3 different packs of planetary analog crater terrains. And each of those particular packs involves looking at either the delta fan, the shoreline area around the lake, the inner gullies, as well as the external ejecta blanket and gullies. So this is another kind of research. So we're basically trying to support the ongoing work of the exploration of a crater on Mars as well. So this is the other side, and it's a lot closer. Logistically speaking, it's a lot easier to conduct work there. So to summarize that was the site in Lunar on the left, and on the right, I will not go into detail about that particular site, but also we have salt flats, and there's a great, one of the largest salt expanses on our planet exists there. It's called Kutch, and also there's been several lines of work that have been defined, but we haven't really conducted them already. There's been some work that has already taken place. And India also has 2 stations in Antarctica. So this is just to reflect the fact that we have identified these different Mars analog regions in Indian or Indian operated terrains. I will spend a little bit of time talking to you about the Mars Amity Research Station. So our university is also really interested in analog research, astrobiology, and we would like to make use of a facility that is established at this particular station, operational from next year onwards, in terms of supporting some of the astrobiology research, as well as some of the analog research, which basically would involve both external as well as internal studies inside the station. So far, I've been fortunate to get a lot of support. I've just listed some of the people who are advising as well as leading some of the research streams here. So people like Dr. Chris McKay at NASA Ames was my former mentor, as well as Dr. Jonathan Clarke, there's Carol Stoker, also Jennifer Blank from NASA Ames. They're obviously mentioned as Amity adjunct faculty members, as well as internal research coordinators. And also from Europe, Dr. Bernard Foying, Dr. Charles Coquel, Sanjoy Som from Blue Marble Space, and also Dr. Martin van Kanendonk, and Dr. Darlene Lim, who's obviously a very well-established science operator, planetary science operator, operations research member. And we are in the process of currently assigning responsibilities, developing teams that will actually help in the establishment of the station. So each of these members currently are helping us identify our requirements in terms of what we need to place at that particular station. So our current plan as of now is we'll be establishing the station. So that's where our efforts are right now. We're in the process of leasing land and working with the state government to ensure that all of the permits are in place. It will be a sustainable system. We'll be eventually ensuring that it's completely off the grid. We are producing our own energy from solar, as well as managing our waste. And then we will be inviting, hopefully by early next year, applications for people who would like to be part of that first. It'll be open for 3 months. So we'll be doing 2 rotations of 1 week to 2 weeks. So all of that information will be available publicly by hopefully January or February next year. And it will be a 3-month season, because that's how long you can be, at least for the summer duration in Ladakh. Because right after that, once you get into winter, like right now, in 2 weeks from now, the roads all the way that go up there start blocking up. So unless you have the capability of staying there throughout the year and not having to come back to Leh, which is the closest airport, you can do that. But to start with, at least for the first 2 years, we'll be maybe looking at 3-month rotation. So we'll be establishing things, and then getting whatever else we need to get back. Otherwise, we'll be leaving the main structure there in place. So the next year, in fact, will be quite exciting for us to ensure that we're able to conduct feasibility checks in terms of the systems, as well as do some amount of continuation of the science exploration and the documentation as well. And down the line, we are hopeful to have an ongoing program in similar capacity to what MDRS and High Seas and some of the other stations have. And so we currently have a 3-year plan, which will obviously be extended based on the amount of interest in research. And I should point out that in India, there's a lot of engineering schools and universities, and many students, in fact, visit these facilities at MDRS and other places. And this is actually to also cater for them, to ensure that we're opening such kinds of research, education, and training facilities to allow them to do this work, in India. But having said that, given the uniqueness of the region, Ladakh, and the high altitude environment, we would invite people from all over the world who would like to come and spend time at the station and continue the work that they're doing elsewhere. So just to summarize, I've highlighted the importance of Ladakh as a region for astrobiology and Mars analog research, and these diverse set of sites in high altitude environment. I have announced the Mars Amity Research Station that we're working away towards having it operation from July of next year, and keep watching. And my university website, center website, I'll be posting the link as well in the chat, so you can subscribe to that. And hopefully by January next year, we should be able to announce applications, and hopefully by second quarter next year, we should be in a position to get people from outside of India, as well as Lunar Crater, which is the other site, which is basically crater-based astrobiology research. So I hope I'm still on time, and thank you very much for this opportunity.
Thanks, Sid. Fantastic. And look, that's an amazing talk about what's going on in India in terms of Mars surface simulation missions. Thanks for that again. Look, we'll just move along pretty quickly, if we could, to Dr. Shane Usher, who's a research fellow at the Department of Chemical Engineering at the University of Melbourne. He's got a Bachelor of Science, Bachelor of Engineering, a PhD, all from the University of Melbourne. He's published over 50 research papers. He was also a member of Expedition Boomerang that Guy talked about a bit earlier on in the MDRS in Utah. He's got a particular interest in the long-term sustainability of Martian habitats and life there. Now, an interesting thing about Shane is that he's a world record holder in, he's a rower. So he's got world records in Concept 2 rowing machines from over 100 meters to over 100 kilometers. And he's going to also talk to us about the benefits of exercise, particularly rowing in space. So that might be something which we'll look forward to. So Shane, fire away.
Back in 1969, it all started from my perspective when we landed on the moon. But no one's been back since early 70s. And in my lifetime, no one's landed on Mars. But from that point in time, there's been a lot of effort in terms of, and excitement in terms of these analogs that we've been talking about. And we've been trying to prepare for when we go to the moon and when we go to the Mars for long-term missions. And that's what I've set myself as a mission. How do we make this accessible to more people? And that basically means the cost of these enterprises needs to come down, and also the viability of being outside Earth's protection for a long period. We need to work on that. So what I'm going to talk about today is a bit of research that we're planning to conduct at the Institute of Biomedical Problems in Moscow, and I'll tell you a little bit about that facility. And this is all about rowing in space, and I'll tell you a bit about the reasons why I think that is a good method of exercise to maintain bone density and muscle mass. We're relatively short on time, so I think most of the stuff about me has been covered anyway. But there's one thing that didn't quite get mentioned, and that was that I was silly enough to try to row across the Indian Ocean. And so now I have 2 world records for not rowing across the Indian Ocean. We got most of the way across, and then I had to be evacuated with a medical emergency. And shifting to a tanker is not the easiest thing in the middle of the ocean. But I think I'd learned most of what I need to learn by that time. And then when the crew finished, we got two world records, one for the fastest crossing of the Indian Ocean rowing, and the other was for the longest distance covered. Now, I sort of think one of those should be just mine, because after I left, they slowed down a bit. But there's three main challenges in terms of analogues, and that's looking at minimizing radiation exposure, dealing with the effects of vacuum, and creating some kind of artificial gravity. Now, here on Earth, the radiation exposure and the vacuum are challenging, and most of the analogues that we look at don't involve vacuum. I have some plans for that, which I'm going to talk about tomorrow. But for today, I'm talking about dealing with the impacts of reduced gravity, whether you're in space, on the moon or Mars. And NASA has created a bit of a table or plan for how they're going to get rid of or deal with all of the risks that occur. Particularly at the top of their list is radiation, vacuum, and gravity. And some of the implications of those gravity issues are bone density and muscle mass. And 2 of the facilities that I have some familiarity with, the first one's Mars Desert Research Station, which pictured there, it's a 2002 picture that Guy talked about. And above that is the Institute of Biomedical Problems. That's a collection of pressure vessels, all with an environment that is controlled so that you keep CO2 levels down, has a slight positive pressure, and they conduct long-term experiments there. So I won't talk much about Expedition Boomerang because that's already been well covered. But the missions that they're running in Moscow are called Sirius, and they're a collaboration between NASA's Human Research Program and the Institute of Biomedical Problems in terms of running the program. They've run a 4-month mission last year. They have an 8-month mission, which was going to start this year, but due to COVID, it's going to start in June next year. And following that, they're hoping to run 12-month missions. So they're building up. And in these isolation missions, you can have a time delay, and you are very isolated. So going outside's a little different. There's a whole bunch of features of the missions and the facilities. And one thing that's fairly important to mention is that going outside for an EVA, which all the others do, is that you basically have a moon surface or a Mars surface that you can go out to in this large room. And when I first learned about it, I thought that it'd be depressurized, but unfortunately not. But you still go out in your spacesuit, and you have to go through all the same procedures. And in terms of operating it, it's an isolated environment for 6 people with nominally 3 Russians and 3 international crew members. You have a range of specializations, and they require that you have 2 doctors, a couple of engineers, and a couple of biologists. Most of the experiments they run are biomedical or psychological experiments, but there's a whole range of different things. One of the interesting ones is that they do mess with the environmental controls such that you have different lighting systems, and they're looking at they're looking at the impacts of lighting systems on sleep, such as where we have our night lights for our computer, where they change the hue so slightly to change the blue to red balance. And they're looking at the impact of sleep there. Now, for me, when I was planning to go there, I was told that to get myself into one of these missions, I really need to do three things. One, to learn a bit of Russian, and I promise my Russian is very basic. They said I just needed some basic Russian. I think I'm there with the basic, extremely basic, but I'm making progress there. They also wanted me to have an MOU with an Australian institution and them, and Melbourne University with a bit of deliberation has signed an MOU so that we can conduct research. And further to that, they wanted me to bring some of my own research. And as a chemical engineer, most of the interesting things in that light are kept away from that experiment. So it's all done externally. So I thought, what can help, if I'm going to be in there for 8 months, what can help me get to the other end in good health? And I figured that I'd really want a rowing machine in there. And from a research perspective, what I want to look at is what exercise, hopefully rowing, can maintain the best bone density and muscle mass and get me to the other end in the best physical and psychological state. So what I did when I went there, I had a little visit. Anastasia Stepanova, one of the people there who Jonathan Clarke knows well because he did one of his Mars missions with her, was pointing out that they have six stasis units to put you in stasis, so that the 8 months goes quite easily. Lots of portholes. According to the Institute of Biomedical Problems, NASA has a height restriction that you can't be taller than 180 centimeters. I think there's a good reason for that, because some of the confines with the sleeping quarters there, you'd probably get a crooked neck by the end. But luckily, I'm a lightweight rower and quite short, wasn't an issue. This is the moonwalk area, and these are some of the spacesuits that were provided by NASA. I'll skip through this. Now, this is just one picture there from the guy who did a Mars 500 mission, where he was there for 520 days. And this is a picture of a reunion that he'd had just the week before, which showed that at least 4 of them are still talking to each other out of the 6th. Now, for the exercise program that we have there for this next mission is currently planned to have 6 sets of exercises. So you can have a rotation where everyone rotates through the 6 sets. And what they're looking at is 6 different sets of equipment that you run through. Now, before I talk about that, the project team that I've put together from Melbourne University involves myself, Rowena Christiansen, who most of you know, and Catherine Stock, who is a biomedical engineer. And they've been invaluable in terms of their advice and help in helping to plan this research. In Russia, there's a large team of coordinators there, and we've been also talking with some German and UAE researchers about data sharing, because one of the important things is there's over 70 experiments running simultaneously, and you don't want people doing replicating the same experiment. So some of the data to provide some data for one group and then do the same experiment again to provide it for the other group. So there's a lot of coordination involved there, and agreements in terms of data sharing as well, because that's fairly important that all the I's and T's are crossed and dotted in terms of agreements, especially when you're working with space technology. It's much easier in the medical area rather than in the rocket area, but there's still a lot of protocols to go through and ethics considerations. Now, the exercise program, as I said, has six different pieces of apparatus, and treadmills, two kinds. I'm not sure whether it's the Germans or the Russians who are quite keen on it, but there's a regular treadmill, and I don't know whether this one's called the passive or active treadmill, because you have to do all the work yourself, and you can decide for yourself whether that's passive or active. I think the naming's slightly reversed. I would say that that's the active one as opposed to the passive one, if you have to do the work yourself. There's also two exercise machines, and this one's a bit the Russians versus the Americans. The Americans have a machine, and the Russians have a machine. And nominally, I think one of those might be active and passive as well. And of course, there's the rowing ergometer, which I want to use in the experiments there. And what's important there in terms of what we're going to monitor is we're going to basically set the exercise time as some nominal goals with power output, but they'll be very individualized. And we're going to try to monitor the power output and the heart rate for all of the exercise sessions, which are nominally to replicate the kinds of exercise programs that astronauts and cosmonauts are undergoing on the ISS. In terms of testing, we want to use conductivity scales to measure weight, body fat, and muscle mass, and to do that on a regular daily basis if possible. We also want to look at ultrasound to actually physically quantify changes in muscle mass and bone density. And that's pretty much all I want to talk about. I see that we've come to the end of our time. So I think I'll put it back to Earl White so he can control any questions if we still have time.
Thanks for that, Shane. Look, that was a really interesting talk. But look, thanks to the participants for the sessions this afternoon. There's just been so much information that we'll all have to go away and have a good think about. But it's been really, really quite fascinating. So there's a bit of a break now, and we'll then resume in about 15 minutes or so with Annalie Beattie, which will be talking a bit about living on Mars and what that's going to entail as well. So that's actually a workshop style session. So thanks everyone, and we'll see you shortly.